Okay, so today we're going to talk about cyclohexanes and the difference between cis and trans and axial equatorial. So they're not the same. Axial and equatorial and cis and trans are not the same. So a lot of times I'll see students say, if they're cis, they must both be equatorial. If they're trans, they must both be axial. That's not true. So we're going to talk about that today and the process that I go through every single time to get the right answer on these questions. So what I have for you here is a cyclohexane drawn as if it's in the plane of the page. I'm going to use this instead. So the cyclohexane is drawn modeled as if it's drawn in the plane of the page, okay? And all the purple, I want you to imagine all the purple are wedges. And they're all coming out at us. And so all these purple bonds, so imagine there's a hydrogen at the end of it or a bunch of CH3s, I don't care what you do, as long as they're consistent, they're all cis to each other. And the purple is trans to these white or gray, whatever you want to call them. So now I'm going to draw the white or gray. There are the dashes. So the purple are the wedges, the white or gray are the dashes. The dashes are going into the page, and the wedges are coming out of the page. Okay? That's kind of a little bit messy, so just to have an easier visualization, I'm going to draw all these. Just the wedges, so just the purples are drawn here. There's also below them wedges going into the plane of the page. Okay, so that's our flat cyclohexane. But in real life, cyclohexane doesn't hang out like that, right? Instead, cyclohexane hangs out more in this conformation, what's known as the chair conformation. It's a chair because this side's pointing up and this side's pointing down, and this makes this is the little seat. You got a back and a little footrest. I think it looks more like a pool chair, the lake loungers at the pool, but whatever. So that's the chair conformation. And I want you to notice what happened to these purples that formerly were all pointing up and out at us. Now there are only 3 pointing up at us, and there's 3 that are along the outside, that are in what's known as the equatorial position. So these 3 are in the axial, and these 3 are in the equator, the equatorial. So now I'm going to draw that for you. So this is the chair. We've got our 4 carbons that make up the chair. Oh, I flipped it around. Got our 4 carbons that make up the chair. Here's the back where you can lean. Here's the place where your foot goes, a little footrest. So that's what we have drawn off to the side here. And I'm just going to start with drawing the purples, just like the purples are the wedges I drew up here. So in this back carbon right here, we have a purple axial that goes up. And then we have a purple equatorial back here that's in line. So I'm going to draw it as an equatorial. Then we have a purple axial that goes up. And then we have a purple equatorial that's in line, that's in the equator. Then we have another axial that goes up. So this one's pointed up. And then we have an equatorial. Okay, so now you can see that these cis bonds all to each other alternate. Axial, equatorial, axial, equatorial, axial, equatorial. Okay, so if you were drawing these as wedges, this would be a wedge axial. This isn't proper, but this is a wedge axial, a wedge equatorial, a wedge axial, a wedge equatorial, a wedge axial, a wedge equatorial. Now let's draw all the dashes. So each one of these has a dash that goes with it, right? I'm not going to draw the full triangular dash just because we don't have a ton of space. Those are represented by the gray here in our model, right? So we've got, I'll just start on this same back corner that I started on. Got our chair, the back pointed up, the footrest pointed down. And where we have an axial purple, we must have an equatorial gray. So there's an equatorial gray dash. And then on the next carbon, you have an axial gray, and it's pointed down. So I'm going to point below this line of the carbon. So now you've seen your equatorial gray right here, your axial gray right here. Then you have another equatorial gray. I'm even pointing it down in the same direction it was pointed here. All the wedges are pointed up because they're slightly angled up. The dashes are slightly angled down. And then we have an axial wedge right here. It's pointing down. An axial wedge over here, or an equatorial gray over here. And then finally, an axial gray over here. So these are also alternating. The opposite. Equatorial, axial. Equatorial, axial. Equatorial, axial. So you can see how cis and trans and equatorial axial are related, but they're not the same thing. If you have a 1,2 cis bond, one's going to be axial, one's going to be equatorial, or vice versa. They don't have to stay in this position, but you can see that. If you have a 1,3 cis bond, you could have two axial positions, or if it's cis and they're both dashes, you could have two equatorial, or if they're at these positions, you could have a 1,3 cis that are both equatorial. So axial, equatorial, cis, trans are related, but they're not the same thing. And you can even see the proper way of drawing this boat chair conformation. Usually professors aren't quite this picky, but if you want to be sure you get like a free response answer right, is you'll see every, 3 of these axial, every other axial is pointed up. So we've got axial pointed up, axial pointed up, axial pointed up, and the other 3 axials are pointed down. Axial pointed down, axial pointed down, axial pointed down. That's because that's what's happening here. Our 3 purple axials are pointing up. Our 3 gray axials are pointing down. Axial up, axial down. Axial up, axial down. Anyway, this just really helps me to see why we draw a boat and chair the way we do, and why some lines are pointing up and some lines are pointing down, and why cis and trans does not mean the same as axial and equatorial. So I hope that helps you too. And just to make sure it's ingrained, I'm going to do some practice problems from chapter 4 so you can sort of see how this plays out practically. Okay. So these are practice problems from chapter 4 in the Solomon's textbook. And the first question is, what is the preferred conformation? Oh, I didn't talk about that. So let me say this real quick. The equatorial positions have more space around them than the axial because they don't have anything nearby them, where the axials their electron density is trapped in this smaller space, where the equatorials have all this room around them, right? So if you have a big bulky group, it's going to go better in an equatorial position. And if you have an option to get all your groups in an equatorial position, that's always better. The equatorial position is always better. If one has to be axial and one has to be equatorial, you want the bigger, bulkier group to be in the equatorial and the smaller, more narrow group to be axial. Okay. Now that we've talked about that, we can do our practice problems. So number 15 says, the preferred conformation of cis-tert-butyl 1-methylcyclohexane is the one in which what? So the way I always start these problems is literally by drawing out the flat cyclohexane, even though it's not proper, and then I mark the 1, 2, and 3, cis-3-tert-butyl 1-methyl. So 1 has a methyl group, 2, 3 has a tert-butyl group. Okay? And then I literally draw wedges. So they both have to be wedges. I'm going to draw the wedge in between, even though it just has a hydrogen on it. All these wedges out. And I start labeling equatorial and axial, because we know they're alternating. So the tert-butyl is a big group, so we want it to be equatorial. You can start with either equatorial or axial, it doesn't matter. The next one is going to be axial. The next wedge will be equatorial, and then axial, equatorial, then axial. These are all just protons, just hydrogens, I mean. So you don't have to draw those all, but now we know our equatorial, our CH3 and our tert-butyl can both be equatorial. Equatorial is more stable, that's what we want. There is another conformation where they're both axial. As long as they're both equatorial or both axial, that's fine. But if you have an option, you always want to go equatorial. So we want something that has 1, 3, and both of them are equatorial. So I'll start with my CH3 there. 1, 2, 3, and this one's also equatorial, and it'll be tert-butyl. So that's our final structure. And then the question doesn't actually ask you for a structure. It's asking for you to say which groups are equatorial and which are axial. So the preferred conformation is one where they're both equatorial. So that right answer is D. Now answer choice C, that is possible. It is a possible conformer, but it's not likely because that tert-butyl group is not going to want to go out of position. And just to confirm this, we can build on our model. So let's say this gray one represents the CH3, okay? So we're putting it equatorial. And then, so that's on carbon 1, carbon 2, carbon 3, also equatorial. So both of these are gray, so that means they're cis to each other. Because remember, we built the model where all these were the same direction. So if you went back to the flat model instead of having it in chair position, there you go. You can see they're both pointing towards you. They're cis to each other. So that's how I actually solve these problems literally every time. So I'm going to do the same thing down here. It's asking for trans 1,2-dibromocyclohexane. So I start with drawing the flat circle. Trans means one's a wedge and one is a dash. So I still draw all my wedges. So we have 1,2-dibromo. So there's a bromo here, and then there's a bromo here, right? So what I do, I don't label the dash yet. I do all the wedges. So axial, equatorial, axial, equatorial, axial, equatorial. So if this one's axial and this wedge is equatorial, that means that this bromine also needs to be axial. So we need to have them either both axial or both equatorial. It doesn't matter. I arbitrarily start with usually axial, just, I don't know why, habit, I guess. But if it's a 1-2 position for them to be trans, they're both either going to be axial or equatorial. It does not matter which. So we want a boat conformation that has either 1, 2 axial, so that's bromo. The most stable position would be as if they were both equatorial, so like this. They would have more space. Now I'm going to draw this for you. Say this one represents our bromo 1, this represents a bromo 2. So they're trans. One's on the gray, one's on the purple. We're going to go back into our boat conformation. Our chair conformation. So here's our chair. We've got the seat. We've got the one pointing up, the one pointing down. The lounger chair is how I like to see it. And you can tell in this conformation that both of these are in the axial position. These three are both in the equatorial. These three are clearly axial. They're clearly pointing up. These three are clearly pointing down, and then kind of have to zoom out a little to see it fully, but these are in the equator. Now, even though they're both in the equator, one's kind of pointing up and one's kind of pointing down, but they're both in the equator. It's not as stark as the axial positions right here and here. They are still in the equator, but that's how you get a cis and a trans that will both be equatorial. Now, if we change the conformation just a little bit and flip to a different position of the boat, these could be in the axial positions. And you'll see them both in the axial. So that's what I mean about it can go back and forth. They could either both be equatorial or they could both be axial. So let's get our chair in order here. It's hard to flip between the two. Okay, So now you can see we've got our chair, it's the other direction. So here's the part that's pointing out, the back headrest or whatever, the seat and the footrest. And now our bonds are both in axial positions. They're clearly pointing up and down. They're not in the equator anymore. And this one, and this one are pointing up and down in opposite directions. So this represents the up and down in opposite directions. We can see it right there. And this represents the equator. So then our right answer would be anything that has a 1, 2, where they're both axial or they're both equatorial. So this is equatorial and this is axial, so that one's not right. This one's equatorial and this one's equatorial, so this is one of our right answers. We have multiple, so we have to go through all of them. This is equatorial and this is equatorial, so this should be one of our right answers too. So I think the right answer choice for this one should be D, which is 2 and 3. Okay, and we have 2 more practice problems that I want to go through with you guys. If you feel like you've got it and you don't need these practice problems, that's fine, but students kind of seem to struggle with this, so I just wanted to be really thorough. Okay, so this next question is, which conformation represents the most stable conformation of trans, 1-bromo, 4-methyl cyclohexane? So again, I always start the same way. I've been doing this for a long time. This is basically the only system I know how. Dr. Berhe or your instructor might have a different way of doing it, but this is how I always do it. So I'm going to draw all my wedges. I'm going to label them axial, equatorial, axial, equatorial, axial, equatorial. It does not matter. And then it's going to be 1, 4. So 1, 2, 3, 4. So they're trans, so I'm going to go ahead and draw the dash. So we've got 1 axial. This wedge is equatorial, so the dash needs to be axial. So we're either going to have 2 axial or 2 equatorial substituents to make trans 1-bromo 4-methyl cyclohexane. Everything likes equatorial better, so I'll go with equatorial. We've got an equatorial bromo. That's a carbon 1, 2, 3, 4, and an equatorial CH3. So the most stable conformation is equatorial. A possible conformation of this would be if they were axial, 1, 2, 3, 4. It could look something like this. But that's not what it's asking. It's asking for the most stable. So, and it doesn't seem like they give you that one. I guess they're not trying to trick you too hard. So 1, 2, 3, 4. These are 4 apart, and they're both equatorial. That's a possibility. 1, 2, 3, 4. These are 4 apart, and they're equatorial. That's also a possibility. These are 1, 2, 3. This is 1, 3, not 1, 4. So that's not even the right structure. 1, 2, 3. 3 again. And 1, 2, 3, 4. Oh wait, I just realized this one is axial, so that's not right. These are both equatorial. This is pointing straight down. That's axial, so that's not right either. And this they're 4 apart. This one's axial and this one's equatorial, so that's not right. But so this is kind of a tricky question. But if you can count to 3 and know that it should be 1, 3 instead of, or it should be 1, 4 instead of 1, 3, you can eliminate 2 answer choices and narrow it down to 3 right away. So that improves your choice on an exam without having to draw this whole thing. But I always draw this because otherwise I get questions wrong because I am not super attention to detail. So I will make small mistakes like that pretty regularly. So the right answer on here is answer choice A. Okay, and then which of the following could be described as cis isomers? So I'm just going to draw this out. My cis roadmap or chart, whatever you want to call it. And you could do all dashes if you wanted, if that's easier for you. You could draw them all out. Like you could go through and draw dash, 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 whatever you want to do. Whatever makes sense to you, you've got to develop your own system. Okay, so these here are 1, 2, 3, 4 apart. So 1, 2, 3, 4. They need to be axial and equatorial. Both of these are equatorial, so this is not right. So when we're at 1, 4, 1, 2, 3, 4. For it to be cis, we need one axial, one equatorial. So that's not right. Here we're at 1, 2, 3, 4. Okay, this is 1, 4 again. So in black, I've got 1, 4 drawn. 1, 2, 3, 4. One's equatorial, one's axial. I think that's a possibility. Okay, 1, 2, 3. For 1, 3, if they're cis, 1, 3 instead of 1, 4. So 1, 3 is in pink. They both need to be axial or they both need to be equatorial. One of these is axial and one of these is equatorial, so that is not right. This is 1, 2, 3. Again, one of these axial, one of these equatorial. Not right. I was about to say axiatorial. That's not even a real word. And then number 5, 1, 2, 3, 4. So this is 1, 4. So one's axial, one's equatorial. So that one is right. So the two right answers would be 2 and 5. So that means the right answer is answer choice B. Okay, so that's just a quick review of axial and equatorial. I hope that was helpful for you guys. This really helped me figure it out. I was confused for a long time until someone showed it to me this way. So I hope that helped you. And if you have any other questions or things you need help with, please feel free to reach out to me.